about a couple of things before we jump into our notes. Hopefully a few other people will filter in. So your first exam is coming up next week. Sorry if you forgot, I'm gonna have to now be reminded of this. It's on Thursday, so we have this whole week, and then Tuesday, and then your first exam's on Thursday next week. We are hopefully going to get through at least 2-3, if not, I think the one after that would semi-obviously be 2-4, but I can't remember if there's a 2-4 or if it jumps into chapter 3. No, 2-4. So we might get up through 2-4. We'll see how it goes. But hopefully at least up through 2-3. I plan on getting a review packet out to you guys as soon as I can, hopefully by Friday. It might take until the weekend for me to get it completely done, but I want to get that out to you guys with a list of topics you want to look over and some practice problems as well. One thing that is already up on Blackboard, so where do I want to go to this one, pop over here. If you haven't seen it already, I mean, some of you might not need it, but I know 1-2 was a bit of a bear, if you will, and I will be quite honest, I don't think I explained it very well at the time. So there's some extra information for 1.2 with all those, you know, the rules and how we use them and that stuff. So there's some extra practice in the answers to some practice, and then I also recorded some videos. The first one's just like the general idea about how they work, and then I went over the 2 questions from quiz 2 in a little bit of detail. So if you want to look over that, if you're still really struggling with 1-2, especially with the exam coming up, there's that. I think that was the only 2 things that I had to say. I will talk more about the exam as it gets closer. For those people who might be quarantined and isolated, I'll have to talk to y'all separately. I'll send y'all an email. But anyway, we'll talk more about that as it actually gets closer to next week. So we started, last time we started 1.5, and this is the last section of chapter 1. So we're going to go through the last 2 examples, and then we're going to move on to section 2.2. We're going to skip 2.1 and come back to it later. So we were talking about all these different methods of proof. So we started talking about, and I should change this over before I forget. And so we were talking about, we started with direct proofs, which was essentially just one thing follows from the other. So we did a couple of those where you kind of come off to the side, excuse me. Come off to the side, you play around a little until you figure out what you want. Why do you keep doing that? Stop it. And then we went over last time the contraposition. I think that was last time. Yeah, we started with contraposition, which is when we switch to the contrapositive statement, the not Q implies not P. We prove that directly, and then thus we can get the original because contrapositive is equivalent. And then we started talking about proof by contradiction, and we went into the semi hard to follow, I'll be honest, example of why the square root of 2 is irrational. So we're going to pick back up in proof by contradiction. Whoopsies. So a little reminder of how the proof by contradiction goes is we assume that the thing we start with is true, and then we're going to suppose that the ending is false, and then we're going to come to a contradiction. I will say with these ones, with the proof by contradiction, these ones can be, I don't want to say a bit harder, but a bit more wishy-washy, if you will, in the middle. Because with the direct proofs, and therefore the proof by contraposition, we kind of have a goal in mind. It's like we start with all of this stuff, and we know we want to prove that, you know, something is even, or something divides something else, or something like that. We kind of have a goal in mind. Or with these proof by contradiction things, we don't exactly know what contradiction we're going to get. We're just trying to find a contradiction. So I think that also adds into a bit of the struggle with doing these proof by contradictions, because you don't exactly know where you need to go. You just kind of got to mess around with things until you come out to something that's false. You don't really have a set path that you're really trying to get towards. But let's go down to this other example that we haven't gotten to yet. This we've actually technically already proved. I think we proved it in contraposition, but we can also prove it by contradiction. So let's see how we can actually reprove this in terms of contradiction. So let n be an integer. If n squared is even, then n is even. So as always with proof by contradictions, we're going to start by saying we're going to assume the things we're given and the hypotheses are true. So we're going to say let n be an integer and assume the hypothesis is true. So assume n squared is even. And then we go into our kind of contradiction setup. For the sake of contradiction, let me reshare this one more time because I think more people have come in and Teams can get weird. So for the sake of contradiction, assume the thing that you want to conclude is false. So if we want to conclude that n is even, we're going to say, for the sake of contradiction, assume n is odd. That is, n is even would be false. And so that's what we have to start. So now let me come off to the side and we're going to kind of do our scratch work. Let me remind ourselves what we have. So I'm kind of literally going to bullet point what we just had. N is an integer. N squared is even. And n is odd. That's kind of the stuff that we have to work with. So now we have to somehow work with this stuff that we have to come to a contradiction somehow. Well, so n is even, but n squared is even, but n is odd. So let's try to manipulate that n squared, knowing that n is odd. So if n is odd, I can rewrite n squared as some 2k plus 1 squared. Right, because that's the definition of odd. So let me see what happens when I start messing around with this a little bit. Well, let me expand that out. If we FOIL that out, we're going to get 4k squared plus 4k plus 1, where this comes from 2k plus 2k. So now I have this idea that n squared is even. But if I start looking at this, I have this plus 1 at the back, which doesn't look like that's going to end up giving me something that's even. That looks like a setup for it being odd. So if I could actually show that this setup is actually an odd number, I would reach my contradiction. I'm using all of this stuff that I have, n squared. I just replaced that with the 2k plus 1 because n is odd. We're assuming that that is a thing. So if I rearrange this, if I try to find some 2, let me use z instead of k, some 2z plus 1. Well, again, I have that plus 1, so let me just not touch it. Can I somehow get 2 times something from the rest of it? And I can, because they've both got 4s in there, and so they're both divisible by 2, so I can factor a 2 out. 2k squared plus 2k. What am I doing? Whoop. Almost ran out of space there. So essentially what I've done is I've manipulated what I started with, and I've come out to, this is an odd number, right? That's the setup for an odd number. But I said that n squared was even. It can't be even and odd at the same time. That's my contradiction. So I started with the fact that n was odd to rewrite n squared. I messed around a bit and then went, hold on, n squared is odd then. But n squared can't be odd because n squared was even. So we've now kind of reached our contradiction. And again, we didn't know that that was going to happen right off the bat. We didn't, well, maybe you did. I don't know. We weren't sure what was going to happen. We didn't really have a path. I just started kind of messing around with what I had. And I wanted to find something that can't be true. So essentially now I have this setup for essentially the bulk of my proof. If I just essentially rework all of this math that I just did down here, then I can say that n squared has to be odd, which is a contradiction because I assumed it's even. So we can say then there is an integer k such that n equals 2k plus 1. So I'm setting up the fact that n is assumed to be odd, so I can write it as 2k plus 1 for some integer k. Thus, and we show them the calculation for n squared. So we essentially recreate the stuff we just did on the side. We say, well, I can rewrite this as some 2 times something plus 1. And remember last time, we also need to be very careful with these definitions of odd and even, that we need to make sure that the thing that we're finding is an integer, but we have that axiom from way back when that says anything you multiply or add together of integers is another integer. So as 2k squared plus 2k is an integer, n squared is odd. But let me just highlight the contradiction here. We've just found that n squared is odd, but we assumed that n squared was even. And then we essentially just say, this is a contradiction. Oh my goodness. Contradiction. As n squared is assumed to be even. And then usually you should just wrap it up with, okay, then I actually proved what I wanted to prove. Thus, so we assumed for the sake of contradiction that n was odd. We saw that that's not possible because we come out to something that's not true. So it must be the fact that n is even. I'm going to let that settle for a minute or so and see if there's any questions before I move on to the next one. So again, we're not entirely sure the contradiction we're going to get, but we take what we have, we mess around a little bit, and we try to find a contradiction. Let me say something else. Let me do it in a different color so it's kind of like an afterthought. Say you focused on the n squared was even piece. So you decided you wanted to write down that n squared is equal to 2k for something. Like, that's something that I could have written down as well. But once I write that down, I don't really know where to go from that. I don't have anything I can manipulate. I can't rewrite that in any other way. Maybe I should say k1 even. Like that, I can write that down. That would be a true statement if I'm saying n squared is even, but it doesn't help me at all. And the n as an integer doesn't really do anything. There's no definition for, well, there is a definition for being an integer, but not a definition that we can manipulate and work with. So really, you can even look at all of the pieces that you're given. I was getting a bit ahead of myself and just jumping to the thing that was going to work. But then if you recognize that n is odd, gives you this, and then you could replace n squared in terms of that. That's kind of what leads you to your contradiction. So you might not see exactly where you want to go right away. You might start writing down things that get you absolutely nowhere. That's what Scratchwork does. It's why it's off to the side and not actually part of the proof. So are there any questions on that one? Okay. I kind of already gave it some time, so I assumed if there was, someone would have typed it out already. Of course, you can always ask me to go back. So we've got one, oh my lord, one more example in this section. We want to prove the following, and it's going to be by contradiction. Again, on a quiz or exam, I would say prove by blah, blah, blah. If you don't see a specification, if it just says prove the following, you can assume it's going to be a direct proof. But if it's a proof by contrapositive or it's a proof by contradiction, I will specify as such. So prove the following by contradiction, adding on after the fact. For every integer n, if n is greater than 2 and n is prime, then n is odd. Now, you can just look at this and say, well, yeah, every prime number that's not 2 is odd, but we've got to prove it. We've got to give indisputable proof that every single prime that's not 2 is odd. And you can't sit there and list every prime number because you'd never get to the end. So how do we start our proof by contradictions? We assume that what we're given and the hypothesis is true. So we're going to say let n be an integer. And assume n is greater than 2 and n is prime. Now we want to essentially say, for the sake of contradiction, the thing we actually want is false. So for the sake of contradiction, for the sake of contradiction, assume n is even. So it's not odd, so it's even. So let me bullet point what we have again. So n is an integer. Maybe I should stop using arrows because that looks like an n flies. N is greater than 2. And n is prime. And n is even. That's the thing we're assuming for the sake of contradiction. So let me get rid of that arrow. The only one of those bullet points that actually has like a workable definition that we can manipulate is n is even. So let's go ahead and start with that one. So like if I went down these, n is an integer, okay, great, I'll keep that in mind, but there's not really anything I can write down to manipulate in terms of that. N is greater than 2, okay, cool, I'll keep that in mind. N is prime, okay, cool, I'll keep that in mind. The only thing we can really work with is this n is even piece. So that means that n is going to be equal to 2k for some k, right? Some integer k, that is important. For some integer k. Now this one, there's not much manipulation we can do. It's kind of a bit more of a thought process kind of idea. So this is all we have to work with right now. Do we need to subscript? Since I'm not going to have another k floating around, I don't need one. If it makes you feel better to always subscript it, you totally can. But that's more for when you have multiple k's floating around, so you have to differentiate between the two. But that's the only one I'm going to have for this one, so I'm going to leave it off. What was I thinking? Okay, so we don't really have any way to manipulate this. There's nothing else we really know to be able to rewrite this in terms of something else. But let's start thinking about this. So n is equal to 2k for some integer k. Well, I also know that n is greater than 2. Well, if n has to be greater than 2, if I think about that, I can actually, let me write that out. So I guess we can kind of manipulate it like this. If n is greater than 2, well, then 2k is greater than 2. I can divide both sides by 2. That's the thing I can do. So k is greater than 1. Okay. What does that get me? So k is greater than 1. So that means that anything I get from this 2k, if you think about it, since k is greater than 1, no matter what k is, n is now going to be divisible by 2. Like if k is 2, then we have 2 times 2, so that's divisible by 2. If k is 3, we have 2 times 3, so that's divisible by 3, so on and so forth. Absolutely any k value I use now, since I know that it has to be greater than 1, is going to give me a number that's divisible by 2. Right? Well, what does that get me? So I know that n must be divisible by 2, which you can, well, you might say, okay, well, I already knew that because n was even, but we need to get rid of the situation where it also can't be equal to 2. So no matter what value k is, n must be divisible by 2. Well, is that a problem at all? I don't freaking know. If we start looking at what we've got, what else do I have to work with? I haven't used n as prime yet. What does it mean to be prime? Well, that means that the number is only divisible by 1 in itself. I've just said that every single n value we're going to get from this has to be divisible by 2, which means that it's not prime. So since I've just shown that for any k value I use, since k has to be greater than 1, my n value must be divisible by 2, that's going to give me that n is not prime. specifically because if you will, it is divisible by 2. So it's divisible by more than just 1 in itself. That's our contradiction. I'm having these numbers that are divisible by 2, but they were supposed to be prime. That can't happen. So we're ready to essentially set up the bulk of our proof. And I kind of need to explain this in you know, a formal way, if you will. So the first thing I did was I wrote out this n equals 2k, so I need to set that up first. So I need to say that there exists some integer k such that n equals 2k. And then the next thing I recognized is that if n was greater than 2, that meant that k has to be greater than 1. So I can say as n is greater than 2, k is greater than 1. I can kind of make that jump because it's such a, maybe I should avoid the word simple, but it kind of is. It's an easy enough calculation that you can jump right from one to the next. If you are uncomfortable with that, we can totally say, you know, 2k is greater than 2k is greater than 1. Let's just go ahead. Let's just do it all full out like that. Let's have all the details in there. So we get that k is greater than 1. Now I'm in that situation and I don't know if I put a period or not. Sure. Thus, n is the product of 2 and a number greater than 1. I'm essentially setting up that idea that it's divisible by 2, which is the next thing I'm about to write in 1 second. Number great, let me just write the word, Lord Almighty. So, n is divisible by 2. This contradicts, so I guess this is my step 4. This contradicts the fact that n is prime. Because again, the definition of prime is it's only divisible by itself and 1. But here we have, whoops, that it's now divisible by 2 as well. So just make your conclusion. Thus, we had assumed that n is even, so we must have just shown that n is odd. So I'll let that sink in for a second. So again, with these, come off to the side, list what you have, and then kind of use what you have and just talk to yourself. What can you manipulate? What can you rewrite? What can you find? Even if you don't think it's going to be helpful, just start listing all these things that you can say from what you have and just try to come out to something that's not true. Again, I know that's it seems a bit wishy-washy because you don't have kind of a direction to go in. You don't know exactly the contradiction you're going to get. You don't know exactly where you want to go, but you just kind of got to mess around a little bit. Questions, concerns on that one or anything from 1.5 before I head on to the next section? Your homework for tonight was, I believe, just on 1.5. I do believe there were some that were completely fill in the blank, you know, the little essay type questions. As with last time, I think WebAssign's a little bugged where it will kind of accept anything. So don't worry too much about the exact format. Just try to make sure you're getting the idea behind it down. And of course, as always, let me know if you have any questions on it. So we will move on to chapter 2 then. Go over a couple of what? Homework questions? Let me start 2.2 And I'll try to leave 15 minutes at the end and we can chat about homework. But we do gotta get chugging a little bit, but I'll try to chop out those last 15 minutes of class to put aside for that. So we need to know what grammatic and Alphic are as well as what? Is that something from the homework? What is frumpable? Okay. No. Was it just a strange definition where it said let frumpable be something and let grammatic be this and let Alphic be this? Did they like define them to be new definitions? In that case, no. You would only have to know the ones I've presented in class. So it is in the textbook, sort of, but I think they have definitions of their own. I will triple check into that. But in terms of like the exam, I'd be focusing on divides, even, odd, the stuff we just focus on in these notes, as opposed to that. That's great. I mean, yeah. I'll remind y'all, this is the first time I've taught this class, so sometimes things get a little, wait, what's going on? So I did not know frumpable was a thing. I like the word. I'm gonna start using it even though I don't know what it means. Frumpable. I like it. Okay, we can talk about that later. We can look at the homework in the last couple minutes. So chapter 2 kind of takes, it's kind of like, okay, we were just talking about logic and proofs, and all of a sudden we're not talking about proofs anymore. We're talking about sets and functions and relations. So it's kind of like a completely different world we're about to step into, which some of you might like, some of you might not like. Don't know. But here we go. So sets. This also might be something, I know you guys were somewhat saying that the logic stuff felt like nothing you had ever seen before in mathematics. And while usually you don't get that far into sets in, other math classes, so this is kind of the first place where you see it full out like this, it might seem a bit more familiar than the logic stuff. But anyway, so let's start. Once I remember, I gotta change this again. There we go. All right, definitions. So a set is an unordered collection of objects. Now, don't get bogged down with the word objects. By objects, we're usually going to mean variables, but it could also be like, we might consider a set of all USC students, or the set of all fish in the ocean, or something like that. But we can also then consider the set of all even numbers. We do not allow repetition. So if you wanted to say that a set includes, if you were talking about the set of all even numbers and you started to list them off and you said 2, 4, 6, 8, 2, 6, 10, you repeated 2 and 6, we wouldn't allow that. Everything in the set should only be listed once. An element, which is also called a member sometimes. So an element of a set is an object in that set. So essentially you have a collection of things and each individual thing would be considered an element. No, excuse you. So for example, I could say consider the set of all lowercase letters in the English alphabet. And of course we could write them out as A, B, N, So there's our letters. There's our lowercase alphabet for English. So if I were to write this out, this right here is going to be the name of the set. So I could also refer to this set as A, and then I would just start calling it set A. And then all of these pieces here, oh no, I did a typo. One of those should be an N. ZDFGJLMN. That one should be an N. So that would have been bad if, so that should have been an N. But if that wasn't a typo and I had M, that would have been bad because I would have had the same thing listed twice. But that technically is a typo. So each one of these individually is an object, an element, sorry, an element. It's an object in the set, but it's called an element. Now, the other thing in mathematics is that you should be careful because if you write capital B, that is not the same thing as lowercase b. So you can kind of think of mathematics as being case sensitive. So if I were to tack on, some extra elements in this set, having these capital letters would be completely different elements than the elements I already had. So if you ever have capital letters versus lowercase letters, they mean completely different things. So be really careful about that. Oh my God, why do you do that? So some notation. Now some sets, any set, sorry, we can essentially describe by listing the elements like we just did in up here. So we can list out literally all the elements. Sometimes you can't list literally all of them. Say I said the set of all even numbers. But if you wanted the set of all even numbers, let's say, for example, we wanted even numbers. And say I want to name that set E. I could start saying 0, 2, 4, 6, 8, but then eventually I'd have to stop because I can never list all of the even numbers. And in fact, the negative numbers are even as well. So I probably should have it instead. The better way to list it would probably be something like -2. Let's start with -4. So I have some more. -4, -2, 0, 2, 4, 6. So sometimes you can't list literally all of them, but you can kind of give a list and then just add some ellipses at either end. With ones like those, you do kind of need a bit more of a pattern. If there's no pattern going on, then you kind of need to list all the elements in the set. And if there's no pattern, then there should be a finite number of them, so you should be able to list them all. But we can list them like that. But in some cases, we also have that sets might have a common property, like all of them are even. So we can use something called set builder notation, which looks like this. So for instance, let me write the example for even, but then let me explain it a little better. So if I wanted to do the set for all even numbers, I could say that all of the even numbers are going to look like x, such that x equals 2k, for k being an integer. And I'm going to explain some of these symbols in a second. So this is another way that I could write the exact same set, but I'm listing it in terms of a property of all of the elements instead of actually listing out all of the elements. So let me talk about some of this stuff in here. Let me do it in a different color too. This right here, this little bar, you kind of read that as such that. So I would read this as x such that x equals 2k for x in the integers. So these other ones we're going to kind of lay out in some tables right now, so I'm not going to point them out there. So this symbol right here, this guy, this means is an element of. You can also say is in as well. And it's essentially saying that, so let me say k, let me just bring out this example right here. This would be k is an integer. And we'll list the integer symbol in a second. So that's essentially saying that the thing on the left is contained in the set on the right. So there's always a set on the right and essentially an element on the left. So that would say that k is an element of the set that is the integers. So for example, in the ones we were writing up here with these even numbers, I could say 2 is in my set E, or 4, or 10, or 12, or 54. Any even number I could say is in that set E. Whereas if you have this other symbol with just a slash through it, this essentially means is not an element of. Is not an element of, or you could also say is not in. And again, it's always a element on the left and a set on the right, assuming you're writing it in this form and you're not being a weirdo and switching it around. I've never seen these things switched around in my life. Oh my Lord, they are always presented in this way. So I could say, 5 is not an element in my set E because 5 is not even. That makes sense? Questions, concerns? Okay. And again, this doesn't just have to be with numbers. We can have the set of all letters. We can have the set of all pets I have in my house. It would be a small set, but it would include my cat and my turtle. And that would be the set of pets that I own, a cat and a turtle. And that can be a set. There are some special sets in mathematics. So here's where that weird Z symbol is coming into play. So if you ever see that Z symbol, and maybe I'll write next to it kind of how we write it when you write it, without having the fancy font just fall out of your fingers. So if we kind of write this little fancy Z, that's going to be the set of all integers. Well, that would essentially be our numbers, anything -3, -2, -1, 0, 1, 2, 3, and so on. The set of all positive integers would then, of course, just be, we don't consider 0 to be positive or negative. It's just 0. It's weird. So this would just be 1, 2, 3, and so on. And then the set of all negative integers would be -1, -2, -3, and so on. The set of what we call the natural numbers, which we kind of write like this, you kind of do 2 lines and then just draw an N like normal. Depending on what mathematician you talk to, there is a huge discrepancy on whether or not you include 0 in the set of natural numbers. I believe your textbook starts at 1. So why is that different from the set of positive integers? Sometimes you'll see this as 0, 1, 2, 3. It depends on who you talk to. If you were to ask me, I would say this. But I believe your textbook does present it essentially as the same thing as a set of positive integers, just starting at 1. If for some reason I wanted you to include 0, I would be very specific about that. But most of the time, I usually avoid using natural numbers because of that discrepancy. We write the negatives, is it okay to do it in the direction like not? So do you want to do that would technically be okay. I would judge you a little bit, but it's all right. The only reason I would judge you is because if you only have one set of ellipses, I would say put the one set of ellipses on the right side. If you have 2 set of ellipses, obviously there's no choice. But no, this is technically correct. Just looks a little silly in my opinion, but that's okay. Then we have the set of rational numbers. If you're going to write this in person, I personally just write a Q and then just kind of give it a little slash. So the set of rational numbers is essentially anything you can write as a fraction. So how we're going to say this is we're going to say it's some m over n such that m and n are integers. And we have to make sure that the denominator's not 0. So that's kind of the first one that we're kind of forced to write in kind of that property way instead of just listing them all out. Because really, you can't really even get a general pattern for all fractions. You could say, well, what if I write 1/2, 1/3, 1/4, 1/5? Well, that's not going to get things like, it's not going to get the point across of things like 2/5 and 5/52 and all that jazz. So we rather write this one in kind of that property setup where we're just say it's going to be a fraction such that the pieces of the fraction are integers and n can't be 0 because dividing by 0 is impossible. It makes the world explode. That's how 2020 is going to end. Someone's going to divide by 0 and everything's just going to disappear. And then the set of all real numbers, kind of just give it a double bar and then do a regular R. The set of all real numbers. Now this one doesn't really have a set notation because it's essentially just any number. There's really no set notation for real numbers. And so this includes things, so this includes your integers, your rational numbers, your natural numbers, because natural numbers are integers. So this includes everything, but then it includes things like pi and e and, you know, irrational numbers like square root of 2. It includes absolutely any number you can possibly think of as a real number. Okay, so that was just kind of definition-y. So now let's get back to some more set definitions and ideas. I need to blow the laptop a little bit. So now we have to talk about the idea of what's called containment. So just above, we talked about how to write that an element is inside of a set, but sometimes you essentially want to say that you have one set that is kind of contained in another set. Every element of this one set is also an element of the other set. So if I want to do something like that, so let A and B be sets. No, that's too far. Let A, B, and, oh my gosh, my English. Let A and B be sets and related so that all of the elements of B are also elements of A. So every element of B is also an element of A. So we would say that A contains B. Now, A might have more elements than B does. That's fine. The only thing it needs is that every element of B has to be an element in A as well. So we have a couple symbols for this, and these ones can kind of go, you know, both directions here, as opposed to the element of, which is usually always written as element, symbol, set. So if we have this symbol, this is going to be read as, sorry, my screen, nope, that's the wrong one. My screen got away from me. There we go. This would be read as is a subset of, and I don't know why I wrote it up that high, there's nothing else I was going to say. So is a subset of. Pardon me for just 1 second. What did past me want to do for set notation? Why do I not remember? Oh, if X is an L, so nope, let me start here. So say I say A is a subset of B. Make that look more like that. A is a subset of B means if X is in A, then X is in B. Whereas if we flip-flop it around, it would now be read as contains. So if A contains B, that essentially flip-flops it around. If X is in B, then X is in A. Think of inequalities. So just like with, you know, less than or equal to and all that jazz, essentially it's going to open to the larger set, or possibly the larger set. So whichever way it's opening is the one that essentially includes all of the elements of the other. So it kind of works like an inequality in that way. So what do I mean if I say, you know, kind of that symbol, and this one can go both ways. We're just not going to list it out twice because it'll mean the same idea in both directions. Just depends on which way it's facing. This would be is a proper subset of. And what that means is it's kind of again, like an inequality, we no longer kind of have that equals to bar, if you will. So this is essentially saying, so if A is a proper subset of B, then if X is in A, then X is in B, but essentially the sets are not the same. So B has to contain some elements that A doesn't have. Now, note that if A is a proper subset of B, then A is still just a general subset of B. It's kind of like if you have X is less than 1. Well, you could also say X is less than or equal to 1 and kind of still get away with it. So that's kind of what is happening here, is if you don't have that little bar on the bottom, you're saying that it is a subset, but they aren't the same thing. Whereas if you have the kind of bar underneath of it, it is possible that those two sets are actually just equal sets. And then these last two are essentially just saying that they're not a subset or does not contain. So is not a subset of and does not contain. So essentially, if A is not a subset of B, I should say there exists an X. That hasn't gone away technically. There exists an X such that if X is in A, X is not in B. There might be some overlap between the two. There might be some elements of A that are in B, but there's at least one of them that's not. And just like same idea, just the opposite direction essentially. There exists some X such that X is in B, but X is not in A. So these are essentially going to be symbols to allow us to kind of compare sets. So let me try to get up through there because I said I would leave a couple minutes. So let's say, for example, we have these two kind of silly sets. So A is the set of eggs, cheese, bread, milk, and ham, and B is the set of eggs, milk, and bread. Well, if we notice, eggs, milk, and bread are all elements of A. So we would say that B is a subset of A, or you could say that A contains B. And I personally will never care one over the other, whichever way you personally write it. I usually default to is a subset of. We could also say that B is a proper subset of A, because there are elements in A that are not in B, so they're not the same set. So since they're not the same set, I could also say that it's a proper subset as well. Saying that it's just a regular old subset is not incorrect, but it's just kind of a stronger statement to say that it's a proper subset, which essentially allows us to say one is contained inside of the other, but they're not the same set. Questions, turn? Okay. Well, let's consider the integers versus the real numbers. One of them contains the other. Is that the integers contain the real numbers, or that the real numbers contain the integers? So which one contains all of the elements of the other? If you think about it, so we're comparing integers to real numbers. So every integer is a real number. So since integers are real numbers, that would mean that the integers are a subset of the real numbers. In fact, it's a proper subset, but I usually default to just the regular subset notation. But not every real number is an integer. Of course, you got fractions, integer. You've got fractions, you've got pi, you've got square root of 2. So the real numbers are definitely not a subset of the integers. And of course, again, we can write that in the opposite direction. They all mean the same thing. It just depends on which way floats your boat on. Now, if we go back to predicate logic, so I said we're stepping into a slightly new world, but we are still going back to that every once in a while. So let's say that I want to say in predicate logic that every integer is a real number. So I could say for all x, if it's an integer, then it's a real number. So I could say if x is in the integers, so we do kind of need that element symbol here. So if x is an integer, then x is in the set of real numbers as well. So we also kind of have this overlap a little bit, or we can use the symbols here as well. Oh my goodness, 2, is just so long. All right, I'm definitely going to do this next definition. So this symbol here, this little kind of 0 with a slash through it, is the notation we're going to use for something called the empty set. Now, the empty set is the set that contains no elements. It's empty. So literally, it's the set that has nothing in it. So also, please don't use, some people, you know, like to write their zeros like that. Please don't do that if you do, because I will always read it as the empty set, and that's not good. And sometimes we're going to need zeros and the empty set symbols in the same thing, and that's always going to not end well. So it's kind of vacuously true that the empty set is a subset of any set S, which is exactly what this is saying just in predicate logic. For absolutely every element, if x is in the empty set, which would mean that x is nothing, then x is also an element of S, which means that the empty set is always a subset of any set you have. Because any set I give you, you could just say, well, I'm just not going to take any of those elements. I don't want any of them. Then you've got the empty set. Okay. I know it's a weird idea to have a set with nothing in it, but that's what it is. I think I'm going to finish this page, and then, yeah, that'll be enough, I guess. Maybe. We should really continue on, but it'll be all right. Actually, I might. Sorry, I'm babbling. I might jump to one last definition after this last piece, and then we'll do some time for questions. A lot of times with sets, you'll see things where they draw some Venn diagrams to try to get some things across. So we can use Venn diagrams to represent sets. We're usually gonna just draw a set to be a circle. And then the inside of the circle would be all of the elements. And so we're gonna use these circles to kind of demonstrate some of these other ideas that we have for sets. So say for the following definitions, A and B are sets. We're gonna have something called the universe. So the universe is the domain or the set that contains all elements being considered. Come on. Oh my goodness. So say I went back to the idea of my set of even numbers. You could say that the universe of that would be the set of real numbers. I'm considering all numbers and just restricting it to the set of ones that are even. Usually the universe has to be spoken. It has, well, given to you. Sometimes it can be assumed by context, but a lot of times it will also be stated as to what the universe is going to be taken to be. The complement is the set of elements in the universe, but not in a given set A. And I'll kind of draw a picture to try to illustrate that in a second. And this is usually going to be denoted by, I really want to say A prime, but that's not really how you would read that. So we'd write the complement of A in that way. I'm going to call it A prime. I don't know what else to call it. So how we would kind of depict this is we would kind of have this box and we would say that the entire box here is going to be the universe. And then I'm going to have some set A that's going to be inside the universe. And then so I've got some, values out here that aren't part of the set that I'm given, but are part of the universe. So I've got all this, green material out here, if you will, that I'm writing dashes through. So we'd have that the white circle, so the white inside the circle essentially, is A. And then essentially that dotted area that I kind of did in a dark green, that kind of looks not green, but that dotted area is A prime. It's everything in the entire universe, but not in A. So there's kind of like this large set, that's the universe, and then you have the smaller set, which is inside of it. Anything that's not in your smaller set, but is in the universe is considered A prime, the complement. Wait, oh, no wonder. No, what is happening? I'm being an idiot. That's what's happening. So let's say, for example, you took the universe to be all integers. And then you took a set A to just be 0, 1, 2, 3, 4, and 5. And that's all you have in A. Then your A complement would have to be absolutely every other integer that's not 0, 1, 2, 3, or 4, or 5. So we'd say, going backwards, we'd have -3, -2, -1, but then we'd have to jump to 6, 7, 8. So essentially, it's everything that's not in A, but in the universe. I'm going to define 2 more things, and then I'll stop. Because I think that'll get you at a decent spot if you want to start your homework for this coming week. Before Thursday when we keep going. Can I flip that a little bit? There we go, while I write this next definition. We have something that looks like this. A kind of U symbol, B. There we go. So this is the set containing all the elements of A and B together. So everything in A and everything in B, and this is going to be referred to as the union of A and B. So I would read this symbols, I would read that as A union B. So if I kind of draw that out and stop spazzing out. If I want to write this kind of in a Venn diagram idea, so let me also just write down A union B, because that's how we would read it. So say I have 2 sets, A and B, and maybe there's some overlap, maybe there's not, but let's just assume they kind of look like this. Maybe there's nothing in there, but. So the union would essentially be everything in A, but also everything in B. So essentially anything that's in either of those sets, whether or not they overlap or not. So maybe I do another one where they don't intersect at all. And it would still be absolutely any element in A and any element in B. It's just everything that's included in one or the other, or both. Whereas the next idea, which is where I'll stop, is we have A, and kind of you flip that union over. That's not an N. It kind of looks like it has a tail on it. It's just a upside down union, if you will. So this is going to be the set of elements that are in A and also in B. And this is going to be referred to as the intersection of A and B. So if I want to draw, so let me say A intersection intersects. We usually say just intersects B. You can say A intersection B. That would technically be fine. So if we have 2 sets, so all of the elements in A versus all of the elements in B, the elements of the intersection would just be where they overlap. So if they don't overlap, then the intersection is empty. But if they do overlap, whatever elements are in both sets are an element of the intersection. So I'm going to stop there. Oh, in exactly 15 minutes. Ooh, go me. So that we can spend the last 15 minutes talking about the homework a little bit, since people want to do that. So let me pull that up. Yes, there's lots of symbols. Lots of symbols. Any questions on 2-2 so far that we've gone over? So we'll, Lord, 2-2 is such a long session. We will hopefully finish it on Thursday. So your quiz on Thursday will be sets. It'll be this idea, and we'll go through some examples next time. But essentially, you'll want to understand this idea of the union is all of the elements. So let me do one example really quick. So not those. So those are something different. So kind of a side note over here. Say let A be, I don't know, 0, 1, 5, 7, let's bring an even number in there for the giggles. And then B is -2, -1, 5, 3, 7, 11. So they don't have to be in order either. If I wanted A union B, well, I'm going to regret doing this many symbols, but I essentially need to take absolutely every element of A, write it down, and every element of B that I haven't already listed. So I didn't already have -2, I didn't already have -1. I already had 5 though, so I'm not going to write that down again. We can't repeat. I didn't have 3, I had 7, and I didn't have 11. If you want to do it at first where you just write them both out and then you go back and you delete the ones that you've rewritten, that's perfectly fine. And if I wanted the intersection of the two, well, what do they have in common? The only 2 elements they have in common are the 5 and the 7. So their intersection would be 5 and 7. So yeah. Does anyone have a particular question from the homework they wanted to talk about? These symbols, you're going to want to memorize. We use them so often that I don't think you would need them anyway, because how much you use them, it'll just be engraved in your brain. Let me not lie to you, but I think, okay, there's really only 2 more symbols that we have floating around that we haven't talked about yet for sets. But again, with problems with sets, they are used obnoxiously often that you just kind of are forced to memorize them. So you will have to remember what those are. Did anyone have a particular homework question, or should I just find the one that had whatever that word that I liked was? Frumple. Number 17. Consider the following definition is frumpable. And square. 6 items. 3 all frumpable numbers are odd. Okay, I think that one of the numbers in this, oh, I don't have my OneNote open. That'll be, come here, OneNote. And let me, sorry, just give me 1 second. Done, done, done. And then I need to share. Where are you? OneNote. So I think the numbers are slightly changed, so that would definitely mean that frumpable isn't an actual definition, because for me, it defines frumpable as an integer n is frumpable if n squared plus 6n is odd. But it's highlighting this number for me, so that assumes that it's different for different people. But it's going to be the same idea. So we want to prove all frumpable integers are odd, and that piece should be the same for everyone, is that we want to prove that they're odd, because the only thing, again, that's highlighted is that 6. So we have, suppose, I don't want to write in red anymore. Suppose n is an even integer. So n equals box. So, well, what does it mean to be an even integer? It means we have it equal to some 2k for some integer k. So that gets rid of that first blank. And then we have then n squared plus 6n equals our second box. So let me kind of come off to the side and do that. So if we have that n is equal to 2k, then kind of side work, we'll have 2k squared plus 6 times 2k. They wanted a bit simplified though, so we'd end up with 4k squared. Well, actually, I don't know if it would take it in unsimplified. I don't know how much give WebAssign has as opposed to some of the other ones I've worked with. So we have that this is equal to 4k squared plus 12k. And then it has that it pulls out a 2. So what happens if we pull a 2 out of this? We'd get 2k squared plus 6k. So this next box, since we have to pull out a 2 of what we just had, we'd have 2k squared plus 6k. And then so we have something, so we have 2 times, this thing. And then it says is what? Well, since it's 2 times something, that means it's even. Obviously, I've been thrown off slightly. What is this doing? Prove all frumpable numbers are odd. Oh, it's doing it by, obviously, okay, sorry. No, it's doing this by contradiction, okay? Because we want to prove that if n is frumpable. Sorry. I've become flustered. I should have written the whole definition out because I'm going to need it. The definition of frumpable is given to you to be a integer n is frumpable if n squared plus 6n is odd. I can rewrite this as if n squared plus 6n is odd, then, oh my god, n is frumpable. And that's something that's come up on some of your quizzes a lot, is you're using the if in the wrong position. Essentially, wherever the if is, the thing that comes after it would have been the hypothesis of an implication. So we're essentially saying if n squared plus 6n is odd, then n is frumpable, even though it's phrased as an integer n is frumpable if n squared plus 6n is odd. So what they're doing is then they're asked to, so sorry, I did this a bit. So prove frumpable numbers are odd. So you want to show that they're odd, but they start that by assuming that it's even. So they're doing this by a proof by contradiction. They just didn't state it as such. So since they have that n is even and it turns out to be not frumpable, then it must be the case that frumpable numbers are odd. So this was actually a proof by contradiction. So I'm sorry, I did that very poorly because I wasn't exactly seeing where they were going right away. But I'm glad it makes sense to the person who asked, so that's good. I guess I see why it does these weird words. Yeah, yeah, no, I don't think that frumpable is actually a thing. Because again, I think the number changes for every single person. But no, we've got some weird words in math, but frumpable is not one of them. So again, sorry, that was technically a proof by contradiction. We wanted to show that all frumpable are odd, so they started with it being even. So they wanted to come to a contradiction, which is why the fact that it comes out to be n is not frumpable is fine. Because if n is not frumpable, but it was even, then it must be the case that if it's frumpable, it must be odd. Hopefully that makes sense. Sorry, I did that a bit all over the place. Sam, you had asked about the homework. Did you have one you wanted to go over? Sam, he's not even here anymore. Okay. Love that. Okay, so he's not here. Well, if anyone else had one, I got 4 minutes. So otherwise, we'll just end. Can you go over 9? Okay. Let's see, what is 9? And I'll try to actually read the entire thing before I look at this. Prove that the sum of an even integer and an odd integer is odd. So start with an even integer and an odd integer. Okay, so this one's just direct. Okay, cool. So what do we got here? We have prove, prove, oh my god, I'm still highlighting. Prove sum of even and odd is odd, paraphrasing. So it starts with let n sub 1 be an even integer, let n sub 2 be an odd integer. So the first thing it essentially wants is for you to write down what that would mean. And they kind of do give you the subscripts that they'll want you to use for each one, because afterwards it says for some integer k sub 1 and for sub integer k sub 2. So well, if n sub 1 is even, so I'll try to keep track of which one was which. So that's even, so that's equal to 2k sub 1. And then if n is given to be odd, that's equal to some 2k sub 2 plus 1. Okay, and then we have kind of the meat and potatoes of the proof they're trying to get us to do. So we have n plus 1 plus n plus 2 equals, so they have blank k sub 1 plus blank k sub 2 plus 1. And then equals blank k sub 1 plus k sub 2 plus 1 is blank. Okay, let's go off to the side and do some scratch work, because maybe I'm not entirely sure where they were going with that. So let's see if I do n plus 1 plus n plus 2, n sub 1 plus n sub 2. So I have some 2k sub 1 plus 2k sub 2 plus 1. Well, that actually does look like what they have right here, so actually that's what they were going for. So the parentheses make me think there was going to be more in there, but really there's not. It's just looking for 2's in there. So we're going to have 2k sub 1 plus 2k sub 2 plus 1. The point that they're trying to make is that both of those have a 2 in it. So we can essentially factor that 2 out. And we kind of leave this plus 1 alone at the back. And we just factor out the 2 of the 2k sub 1 plus 2k sub 2 to get 2 times k sub 1 plus k sub 2. But now since we have this format of 2 times something plus 1, that's exactly the definition of being odd. Anything else? If you don't have anything you want to talk about, you are free to leave. Because we only got 1 minute left, so it's not like I got anything else to go over. So let me type that in the chat so we can find it later. It's going to focus on 2.2. So essentially what we were just working on, so sets. So you're going to want to look at the union and intersections. It's going to be something as you know, we haven't looked at it in like a huge amount of detail. So it is going to be something like, where's my, something like this. Or, you know, I might say something like, does, or is 5 in A? So you'd have to recognize if 5 is an element of A or not. So unions, intersection, element of kind of that idea of this idea of sets. And we'll be going over more examples on Thursday. It is kind of this idea of sets that we just went over. I'm saying the same thing multiple times. Why did I say quiz 2? I don't know. I wrote quiz 2. Yep, I know. I'm just babbling to myself. Number 3? Sure. Let me get back to my OneNote. So we've got A, B, and C are integers, and now that we have this notation, I'm going to use it. So we have A times B divides C, and A divides C. So it starts off with just giving the first part of the proof that I would want to do. And then, so now we want to think about what it means for the definition of divides. So the definition was if M divides N, then N equals, K times M for some K value. So they have the first setup as saying, okay, well, if A times B divides C, well, what does that mean? That mean that C is equal to essentially something times A times B. So they're looking for some integer K, which they kind of set up for you at the back what variable they were looking for by saying for some integer K. And this just comes from the definition, is that it must be that C equals K times A times B. So C equals, and then they have blank A. So we essentially want to manipulate this to look like something times A. Well, there's lots of parentheses floating around, but you can think about this as K times A times B. They're just all multiplied together. So you can also rearrange them and just say K times B times A, and then just go ahead and slap K and B together in parentheses and have that. So now essentially what we've found is we've found the form of something times A, which is exactly the form we need to say that it divides that. To say that C divides A, we need C equals, let me say, X A for some X, since I already have a K floating around. And we're essentially saying that that X value is equal to K times B. So since we can find it as something times A must divide C. Hopefully that made sense. You're welcome. So I have another class at 2:50, but I can stick around for maybe another 5 minutes if people have any more questions they want to go over. I'll stop recording.